Good morning, everyone. I'm Jianyu Huang, a research scientist from Meta. Today, I will present inference deployments and communication implications together with my colleague Xiaodong Wang and Zhao. In April, we launched the Meta AI app powered by Llama 4. I will walk you through a demonstration to illustrate a basic concept about the LLM inference system. We asked it a simple question using a prompt. What is LLM inference? The app will respond to you by generating the answer word by word or token by token. So what exactly is LLM inference? It refers to the process of generating the text or responses based on the large language model. A typical LLM inference system consists of two stages, the prefill stage and then the decoding stage. The prefill stage takes the prompt sequence to set up its internal context for generating the responses. And the decoding stage utilizes and updates the context from the prefill stage to generate the output tokens step by step. The prefill stage processes a single prompt sequence of thousands of tokens at once, generating the key value cache or KB cache for each transformer layer for the large language model. Note that the attention might scale quadratically with the sequence length. So overall, you can see the prefill is pretty computer dominated. Decoding, on the other hand, shows less impact from the compute complexity. Instead, the I/O time of reading memory dominates the overall decoding time. Model weights and the KB cache occupy the majority of the memory during the decoding. With the model fixed, the KB cache size is determined by the sequence length and the large batch sizes. Overall, decoding is memory bounded. So our goal with LLM inference system is to optimize several key metrics. We want a cheaper cost to maximize the GPU utilizations. We want higher throughput to serve more users. The most important thing here, we want to minimize the latency for the best user experience. Time to first token, or TTFT, for prefill, it only delays the start of the output stream. And the time to incremental token, or TTIT, for decoding is more important for overall perceived user experience. So now you heard about the metrics. Let's get to the three types of inference parallelisms at scale. In the remaining of our talk, Chen will discuss about tensor parallelism. You will hear about context parallelism from me, and expert parallelism from Xiaodong. So now I will hand over to Chen to discuss about tensor parallelism.
Great introduction, Jianyu. Now let's take a look at what tensor parallelism is. Tensor parallelism is a way of model sharding. Let's take a look at a simplified example. On the left-hand side, imagine you have an input 1×2 vector x. You multiply by a model 2×2 model weights. You get a 1×2 output y. Now, let's imagine the model weight is too big to fit into one GPU. What do? The natural way of resolving this is you shard the model weights across multiple GPUs. On the right-hand side, we do a row-wise sharding. We put the first row on GPU 0 and second row on GPU 1. And you multiply the sharded model weight with x0 and x1 respectively, and you get a partial result, y out. Now, in order to get the original y output, we have to run an all reduce to aggregate the results back. So basically, tensor parallelism allows us to fit a larger model across multiple GPUs, but we have to introduce an extra collective all reduce here at the end. So here's the trace from our real production end-to-end run. As you can see, highlighted from here, nickel kernel all reduce takes significant portion of the end-to-end latency. In fact, it can take up to 30% of end-to-end latency, and quite significant. That means every 10% improvement of or reduce can roughly give us about 3% end-to-end performance gain. As mentioned in Jianyu's earlier slide, inference contains two stages, prefill and decoding. And message size are in the small and medium range. For prefill, it ranges from 10 to 100 megabytes. And for decoding messages, the message size are even smaller. It ranges from 100 kilobytes to 2 megabytes. So here's the question. How can we optimize our or reduce for such smaller messages? So here we introduce something called direct data access, or DDA for short. DDA algorithm comes with two variants, DDA flat and DDA tree. So as many of you might already be familiar with the classic ring algorithm when we perform or reduce, right? So in the ring, it basically does or reduce in two phases. The first phase, we do a reduce scatter. We send the data from one rank to another, which takes O(n) time. And in the second phase, we do an OR gather, which takes another O(n) time. So DDA flat will let each rank directly access the data from every other rank and perform reduction locally. So this will greatly reduce the number of steps to O(1) by paying the cost of moving extra amount of data. So in fact, we are moving O(n) square number of data compared to O(n) in ring. But since the data size is pretty small, we expect DDA flat will outperform nickel or reduce baseline, ring-based, for smaller messages. But what happens if the message size gets slightly bigger and we can't afford the extra data movement? So this is where DDA tree is coming from. DDA tree will reduce the data in two steps instead of one. The first one, we run reduce scatter, very similar to ring. And the second step, we run OR gather. In this way, we're moving the same amount of data as ring, but we're just moving more data in each step. Now, since the data are not that large, the cost is affordable. So we expect DDA tree to outperform nickel ring-based algorithm for slightly larger messages. Now, let's take a look at how the results look like when we deploy DDA to AMD platform in production. So here's the chart showing the DDA performance gain compared to RICO baseline. The x-axis is the message size, and the y-axis is the DDA speed-up percentage. As you can see from the graph, when the message size gets bigger and bigger, the gain gets decreased. This is expected because when the message size gets bigger, or reduces more bandwidth bound than latency bound. But when the message size is small, say less than 5 megabytes, the DDA gives significant performance boost. It can go up to 50%. And on the prefill side, we implement communication and computation fuse kernel. This bumps or reduce micro benchmark from 10% to 30%. And on the decoding side, we deploy the DDA, which bumps the performance from 10% to 50%. So this metrics translate to roughly about 4% for end-to-end prefill gain and 10% on decoding gain. Now we've learned a little bit about tensor parallelism. I'm going to hand over back to Jianyu to talk about context parallelism.
Thank you, Chen. So now I will cover context parallelism. So we want to first demonstrate our advancements in long context inference in Llama 4, specifically for our 1 million and 10 million context capabilities. Let's start with IROP, which stands for interleaved attention layer. It achieved an infinite context length extending to 10 million tokens. To support this, we have applied various optimizations. Context parallelism, which allows us to efficiently partition the context length across multiple GPUs and multiple hosts. Fast attention kernels, which is a critical component to further accelerate attention mechanism in the kernel level. With these optimizations, we can achieve less than 1 minute for 1 million context length on a single H100 host with 8 GPUs, and also less than 1 minute when we scale that to multiple H100 hosts for 10 million context lengths. There are unique challenges for long context inference. For compute, the dense attention flops scale quadratically with long context lengths, and then attention mechanism dominates the overall prefill time. For memory, KV cache grows linearly with the long context length. And for communication, the overall latency increased when we parallelize that across multiple hosts. To address these challenges, we implemented 2 variants for context parallelism in attention mechanisms. Here is a simple example with 2 nodes. Let's say we have 4 input tokens and split them across 2 CP ranks. CP rank 0 calculates query key and value 0 and 1. CP1 will calculate query key and value 2 and 3. With parse KV algorithm, parse key and value algorithm, we'll switch key and value tensors between these 2 CP ranks. Then we will calculate the attention interactions between query 0 and 1 versus key and value 2 and 3 on rank 0, and similarly for CP rank 1. With parse query algorithm on the right-hand side, we will switch query tensors between these 2 CP ranks. Then we will calculate the corresponding attention interactions. When we extend to more nodes, like 4, it will have more steps to finish this parse KV or parse Q variants. You can see these CP ranks parse query and key value in a ring fashion. So we also call this ring attention. With these variants, we actually achieved a nearly linear scaling with context parallelism. Using Llama 345B model as an example, we achieved less than 4 seconds with context parallelism over 16 nodes, and 77 seconds for 1 million tokens. So now we covered context parallelism. I will hand over to Xiaodong for the SCC parallelism, and then the rest of the talk for conclusion.
All right, thank you, Jianyu. So now let's take a look at the expert parallelism. And before I dive into the details, let's first take a look at why we need that, right? So our large language model has become so big, especially now it's go to sparse, like the MOE architecture, mixture of experts, that we cannot really fit into a single host, which we usually apply the tensor parallelism. Right, so now let's take a look at how a typical MOE model look like. So the input will first go to the attention module, and the output of it will go to a router. The router will dispatch to 128 routed experts. Right? So it will pick one of the expert. That's kind of where the sparsity is coming from. And then the output will be combined with another shared expert sitting on the side, which are the same size of each of individual routed experts. Right? So in total, we have about 129 experts in this model, and this is so big. The active parameter of Llama 4 model is only 17 billion parameters, combining the shared expert and 1 routed expert, and we have 128. Right? So it's kind of really big that we cannot fit. And this is how the expert parallelism work. I'm showing you a very simple example here, where we have only 2 hosts, and each host has 2 GPUs. And we have 2 routed experts, routed expert 0 and routed expert 1, right? And each of the routed expert will be sitting on one of the hosts, and it will be tensor parallel sharded across the 2 GPUs. So on the left-hand side, we see 2 GPUs of host 0, and right-hand side, we see the 2 GPUs of host 1. Then each host will take a different batch of data, right? Batch 1 and batch 2, right? And then, so after the attention module, and the reduce that Cheng was talking about tensor parallelism. But we will go through the router to decide each individual token in that batch will go to which expert. Right? And dispatching is done with the all-to-all collective. So there's the first all-to-all block just to basically to dispatch the input tokens to the target routed experts. And after the routing expert has finished, we will go to the second all-to-all. The second all-to-all is to dispatch back, right? So I finished the routing expert computation. Now let's go back to your original host to finish the computation, to combine your output with a shared expert, right? So these all-to-all can be pretty time-consuming. And we see on this, this real trace that even though we can somewhat overlap the computation, which is happened on the shared expert with the all-to-all on the dispatching, we still see that the all-to-all is exposed, right? There's no computation can happen because of data dependency. And the all-to-all is exposed. It's about 10 to 30% of the end-to-end latency, even after we optimize the overreduce in tensor parallel that Tang was talking about. So how do we optimize this? Right? Obviously, this is not ideal. This is the overhead we pay with expert parallelism. So now let's go to a little bit simple example, again, about how do we dispatching tokens, right? So in this example, we see there's a token A2H on, say, local rank 0 that needs to be dispatched. In this example, we actually show this is a perfect balance, right? So A and C go to rank host 0, E and G goes to rank 1, right? However, we had to prepare for the worst case, right? And in the worst case scenario, all tokens can go to just one single expert. This can happen. And even worse, we have a optimization called CUDA graph. So decode is usually needed this CUDA graph optimization because the kernels are usually very, very small because the batch size is small. We are trying to optimize the TTIT, time to incremental token, because it's really important for user experience. So we can have a very large batch. The kernels are typically fairly small. The CUDA graph optimization kind of get rid of all the CPU overheads, like kernel launch overhead, etc., like Python overhead. All these things are gone. However, it does have an important limitation that the tensor has to be static, right? Like you have to operate on the pre-allocated tensor. And because of the dynamism on the auto dispatching, we have to prepare for the worst case, where all the tokens will go to one expert, right? So we have to pad the output tensor to the maximum possible, which is the dashed line we are seeing here. Which means our auto actually sending a lot of padded data, which is not actually going to be used, right? So our dynamic auto is specific targeting for that scenario. We still pad the input-output tensor to satisfy the CUDA graph limitation. However, we do have another tensor which tells the all-to-all kernel how many bytes you need to send over the wire. So we're only sending the useful data, not the padded data. So in that way, we are saving a lot of traffic, just saving a lot of the bytes sending over the network. The other optimization we are doing is something called persistent all-to-all. So as we mentioned, the decode is actually very latency bound, right? And we see a lot of the slowdowns, overhead coming from the all-to-all kernel because of the memory kernel exchange, networking load balancing, CPU overhead, etc. So we have a library called custom transport, or called CTran, which is going to be open source very soon, right? So we have implement this persistent all-to-all kernel, which get rid of all the CPU overheads. And compared to the nickel baseline, which is the most popular communication library, we are seeing about 22% to 50% of the latency reduction, depending on which size we are transferring. All right. To summarize, we're using tensor parallel, context parallel, and expert parallel, right? Our takeaway is that LM inference, the large language model inference, is really important because it's operating on a latency bound region, right? We want to optimize the latency, which is critical for user experience. We're also seeing a lot of the opportunities in the system level improvements, right? So you see from the context parallelism, we can cutting off the sequence length so that we can use multiple GPUs, even multiple hosts, to deal with 10 million context lengths, which is great, right? In expert parallelism, we are seeing how we can saving the number of bytes sending over the wire with the dynamic all-to-all. These are the system level improvement combined with the networking optimizations. And we're seeing a growing importance of the heterogeneous platforms, right? So we want our technique, communication library, networking optimizations to work across all kind of hardware platforms, whether it's NVIDIA, AMD, or all kind of other custom accelerators. All right. So looking ahead, we see with booming of the large language model, we see a growing importance in the communication space because the model is going so big, you have to use multiple GPUs or even like multiple hosts to serve your model. After we have optimizing each individual kernels, like the all-reduce, all-to-all kernel, we are seeing a growing importance to combining like not just the communication, but also the compute kernel into a single kernel, right? Let's say fusing the all-reduce with the gems. So like in the past, we cannot really fuse them. They cannot run in parallel because they have data dependencies. You cannot do all-reduce until your gem has finished. But you can design a single kernel that's slicing the gem computation. After you compute one slice of the gem output, you can send it over the wire through all-reduce, and then you can compute the next block of the gem output. So this fused kernel, we believe, is the next important area that we should invest in. And that also calls for device-initiated kernels. We want the collectives to be initiated from the GPU kernels or from the device kernels, right, to enable these fused kernel authoring. And lastly, we believe a cloud fabric design is very important. We want to optimize for the latency bound region, like very small packet, getting rid of all the CPU like overheads or network overheads, like as low latency as possible. We see this is very important for the decode stage with the latency bound region. All right, so we believe the future is very exciting. And if you're excited, please feel free to reach out to us, and we will be excited to work with you. Thank you.